Assalamualaikum girls. I am Shamsunisa from Royal Degree College Chemistry Department. Today we'll start Unit 1 Inorganic Chemistry. In this we'll be dealing with Chapter 1, that is Chemical Bonding. We'll study about ionic solids, problems and solvation energy. Ionic solids. In this we'll talk about lattice energy. The elements combine to form a compound only if the overall process results in the lowering of energy. When the elements combine to form 1 mole of the compound, then the net amount of energy released is calculated. More the energy released, stronger is the bond. Lattice enthalpy of a compound is defined as the amount of energy released when 1 mole of the compound is formed due to electrostatic attraction between oppositely charged ions. The energy changes involved in the formation of ionic compounds from their constituent elements can be studied with the help of thermochemical cycle called Born-Haber cycle. For example, the formation of 1 mole of sodium chloride from sodium and chlorine involves the following changes. As you can see here, the reaction, sodium in the form of solid reacting with half mole of chlorine gas, and at the delta H1 amount of energy, that is, as a result of that we are getting the sodium chloride in the form of solid. This is the single step reaction. It may occur in the other steps also, that is sodium in the form of solid when it is undergoing the sublimation energy plus S. As a result of that we are getting sodium in the form of gas. Then from the sodium in the form of gas, after absorbing the ionization energy, the sodium in the form of gas converted to sodium ion in the form of gas. Like that, half chlorine molecule in the form of gas plus half dissociation energy it will take, and as a result of that we are getting the chlorine in the form of gas. Then from that electron affinity it will show, and after that it is converted to the Cl minus ion in the form of gas. So from this sodium chloride which is in the form of solid, after the absorption and utilization or evolution of the lattice energy, it is converted into sodium ion and the chloride ion. Here S is the sublimation energy, D is called the dissociation energy, IE is what? Ionization energy, EA is the electron affinity, U is lattice energy, and delta H1 is enthalpy of formation. And the positive sign, it will indicate what? Energy absorbed. Negative sign, it is equal to energy released. Thus, the heat of formation or the net amount of heat released in the form of 1 mole of sodium chloride is given as delta HF, it is equal to S, that is sublimation energy plus half dissociation energy plus ionization energy plus electron affinity plus U, it is nothing but lattice energy. Using Born-Haber cycle, value of lattice energy can be calculated, or knowing 5 quantities, the 6th can be calculated. Higher lattice energy means stability of ionic compound and greater attraction between the cation and the anion. Hence, compounds having higher lattice energy have higher magnitude of the properties such as melting point and boiling point. The stability of an ionic compound or the stability of an ionic bond mainly depends upon the magnitude of lattice energy, which itself depends upon the following factors. First one is size of ions and second one is charge on ions. First of all, we'll see about size of ions. If the size of ions is small, the inter-ionic attraction increases and the energy of the system decreases. This adds to the strength and stability of ionic bond. Example, The ionic radius of Na plus ion is 0.95 degree angstrom, which is smaller than that of potassium ion. Its value is 1.33 degree angstrom. As a result, the force of attraction between Na plus and Cl minus ions will be more than that between K plus and Cl minus ion. Thus, sodium chloride bond is stronger than potassium chloride bond. Hence, strength and stability of ionic bond, it is inversely proportional to size of ion. Means if strength and stability of ionic bond increases, size of ion decreases. If size of ion increases, strength and stability of ionic bond decreases. Like that. They are inversely proportional to each other. Next is charge on ions. Interionic attraction increases with increase in the charge on ions. Hence, energy of the system decreases. This adds to the strength and stability of ionic bond. Thus, strength and stability of ionic bond, it is directly proportional to charge on ion. It means that strength and stability of ionic bond, if it increases, charge on ion also increases. If strength and stability of ionic bond decreases, charge on ions decreases. They are directly proportional to each other. Ionic bond formation involves decrease in energy. The total heat change in the formation of 1 mole of crystalline sodium chloride from sodium solid and chlorine in the form of gas is delta HF. It is equal to S, that is sublimation energy plus hot dissociation energy plus ionization energy plus electron affinity plus lattice energy. Now we are keeping the values. Delta HF, it is equal to sublimation energy value is, it is the constant value for sodium and chlorine. 108.5. Okay, that is the sublimation energy. Plus half dissociation energy. Its value will be 121.5. Ionization energy value will be 496 plus electron affinity value is minus 394 plus lattice energy value is minus 760 kilojoules. Now in the next step, delta HF is equal to these things we are keeping as it is. Here the plus into minus minus 394, then here also plus into minus minus 760. Now in the next step we are adding these three values, so you will get 726, then minus 394 minus 760 as it is. Now what we are doing, we are adding these two values, that is minus 394 minus 760. So we are adding, we will get the value as minus 1154. Now 726 minus 1154. So you will get the value as minus 428 kilojoules. Therefore, 428 kilojoules of heat liberated in the form of 1 mole of crystalline sodium chloride. Hence, sodium chloride is stable as compared to Na in the form of solid and chlorine in the form of gas. Now we'll see the problems. First problem is calculate the lattice energy of potassium fluoride from its elements by using the following data. Sublimation energy of potassium in the form of solid. Sublimation energy, it is given as 87.8 kilojoules per mole. Dissociation energy of fluorine, D, its value is 158.8 kilojoules per mole. Ionization energy of potassium, which is in the form of gas, its value is given as 414.2 kilojoules per mole. Electron affinity of fluorine, which is in the form of gas, its value is given as minus 334.7 kilojoules per mole. Heat of formation, that is delta HF of potassium fluoride, its value is given as minus 560.5 kilojoules per mole. Here is asking to calculate the lattice energy. You don't know the value of U. Now you see the solution. We know the relation. This formula we are utilizing here, that is delta HF, it is equal to S plus hot dissociation energy plus ionization energy plus electron affinity plus lattice energy. Substituting the values we get. Look at this carefully. Substituting the values we get delta HF value we are keeping here as minus 560.5. It is equal to sublimation energy value is 87.8 plus half as it is we are writing dissociation values, how much it is given, 158.8 plus ionization energy value 414.2. Electron affinity value, the plus we are keeping, then electron affinity value it is in the negative sign, that is minus 334.7. Then plus we don't know the value of lattice energy. So we are finding the value of lattice energy. So what we are doing, think that U we are keeping on that side only, and rest of the thing we are bringing to the other side. This here minus 560.5, it is as it is, and all these values are changing here. Positive it is becoming negative, and negative it is becoming positive. So here minus 87.8, then minus of 158.8, then minus 414.2. Now plus into minus minus, so we are keeping here plus. So this one, the plus into minus is minus, so it is converted as plus. So plus 334.7. So in the next step, U it is equal to minus 560.5, minus 87.8, minus 79.4, minus 414.2, plus 334.7. Now what we are doing, this minus 560.5, minus 87.8, and minus 79.4, we are adding these values and we are keeping minus 1141.9, then plus this one 334.7. Now we are subtracting, so you will get U value, lattice energy value, as minus 807.2 kilojoules per mole. Now we'll see the second problem. Calculate the heat of formation of magnesium fluoride from the elements using Born-Haber cycle. Sublimation energy of magnesium is 146.0 kilojoules per mole. Dissociation energy of F2 is 158.8 kilojoules per mole. And the total ionization energy of magnesium for removal of two electrons, two valence electrons, that is 2184.5 kilojoules per mole. Electron affinity value of fluorine is minus 334.7 kilojoules per mole. Lattice energy of magnesium fluoride is minus 2922.2 kilojoules per mole. Now we'll see the solution. We know the relation here. Look at this formula carefully. Delta HF, it is equal to S sublimation energy plus D dissociation energy plus ionization energy plus 2 electron affinity plus U. This formula we are using. Here we are not using half D, half dissociation energy we are not using, and we are not using simply electron affinity. 2 into electron affinity we are using. Why? Since fluoride ions are involved here, so the 2 into electron affinity will be taken. Okay, and also use D, that is dissociation, instead of half D, as we are using here the fluoride. So now we are keeping the values in that particular formula. Delta HF, it is equal to 146.0 plus 158.8 plus 2184.5 plus 2 into this value minus 334.7, then plus minus 2922.2. Now what we are doing, we are adding these values, these three values we are adding, and we will get the value as 2489.3. Then plus into minus minus, we are multiplying this value with 2, so you will get 669.4. Then plus into minus minus, then that value we are keeping 2922.2. Now in the next step, minus 669.4 minus 2922.2, we are adding these values, so you will get minus 3591.6. Now we are subtracting this value, so you will get minus 1102.3 kilojoules per mole. So here magnesium in the form of gas reacting with chlorine in the form of gas, so we will get the magnesium fluoride. Delta HF, that is heat of formation value, how much we are getting here, that is minus 1102.3 kilojoules per mole. Solvation energy. Effect of solvation on the solubility of ionic solid, that is heat of solution, that may be seen. The heat changes which occurs in the dissolution of salt can be easily understood with the help of Born-Haber cycle, where U0 is called what? Lattice energy of the crystal. The heat of solution can be positive or negative depending upon the relative magnitude of lattice energy, that is U0, and heat of solvation of ions. The heat of solvation is usually negative that is exothermic for highly soluble substances, but not always. The other factor for high solubility is, even though the process is exothermic, is the entropy change which accompanies dissolution. The breakage of crystal lattice is accompanied by a large favorable entropy change, but the ions orient the solvent molecules, causing a decrease in entropy. Using the thermodynamic relation, that is delta G degree, it is equal to delta H degree minus T delta S degree. And we can use this formula also, that is delta G degree, it is equal to minus RT log, that is natural log K. Considering the lattice energy and solvation energy, we can conclude. The first one is the solvation energy and lattice energy are both inversely proportional to ionic radii. And the second conclusion is what? The solubilities of salts usually increase with increasing the size of cations and anions because of more favorable entropy changes on solvation, and also because of polarizing effects in some cases. The effect of charge is usually considerably greater than the size. And the third conclusion is lattice energy and hydration energy are mainly responsible for dissolution of an ionic solid. If hydration energy is greater than lattice energy, the system will acquire minimum energy and maximum solubility. But if lattice energy is more as compared to hydration energy, then the solubility of ionic solid will decrease. For example, sodium chloride is more soluble than magnesium oxide. The solubility of an ionic compound increases with the size of the ion. It is due to decrease in the magnitude of lattice energy than decrease in the solvation of energy of ions, or solvation energy of ions, we can say. For example, lithium fluoride, sodium fluoride, it is showing less what? So here you can see lithium fluoride and sodium fluoride, they are showing less solubility compared to that of potassium fluoride. Potassium fluoride is showing less solubility compared to that of rubidium fluoride. Rubidium fluoride is showing less solubility compared to that of cesium fluoride. It means that cesium fluoride, this ionic compound, it is showing more solubility compared to that of lithium fluoride and sodium fluoride. Here we can see lithium fluoride, it is showing less solubility compared to that of lithium chloride. It is showing less solubility compared to that of lithium bromide. Lithium bromide is showing less solubility compared to that of lithium iodide. It means that solubility of lithium iodide is more compared to that of solubility of lithium fluoride. When one ion in the ionic compound is very small as compared to the other one, a tightly packed lattice is not formed. So its lattice energy becomes less and solubility should become more. Consider the solubility of magnesium sulfate and barium sulfate in water. In these two compounds, sulfate ion is common ion. You can see here magnesium sulfate, barium sulfate, which is the common ion. Sulfate ion is common. While the size of magnesium ion is 65 picometer, which is less than that of size of barium ion, that is 135 picometer. So magnesium ion has higher ionic charge density than barium ion, and magnesium sulfate should be less soluble in water than barium sulfate. But it is not so. It can be explained on the basis that small size magnesium ion is unable to form a closed packed lattice as compared to barium. Thus, magnesium ion gets hydrated to form a packed lattice in sulfate matrix. Due to the presence of water molecule between cations and anion, the lattice energy of magnesium sulfate thus gets much lower than that of barium sulfate. Hence, magnesium sulfate goes in solution much easily and is soluble in water. Thank you for listening my lecture.